Oops. Okay. Okay, midterm 2, March 23rd. And we have at least one more quiz before then. Okay, so we're still on the section on implicit differentiation, right? So it says here, a model for... Okay. Sorry about that. I can turn the projector on. Okay. Anyways, we're on page 76. Everybody with me? Or maybe you guys were just talking because the projector wasn't on. I forgot to turn it on, but it's just warming up now. So on page 76, I believe this is the last problem on the inverse trig section. And it's just asking us, it says a model for the spread of an infectious disease is rho. Okay, well that's all right. You should have this page in front of you, right? Page 26? Sorry, 76, page 76. It'll be up in a minute. There we are. Okay, a model for the spread of an infectious disease is rho. That's rho, it's just a Greek letter. E to the minus Q equals 1 minus A, where rho is the fraction of the population originally infected. Q is greater than 0 as a measure of the disease transmissibility, and A is a fraction of the population ultimately infected. Suppose that initially, that should say rho, I believe. I don't know why it does that when rho should equal 0.01. We'll say that's initially. That is, 1% of the population is infected. Find dA dQ, the rate at which the outbreak size changes with respect to transmissibility. Okay, so rho. So this is 0.01 e to the minus q equals 1 minus a. I'm just not entirely sure why this is in this section, because you think we could just solve it for a right at the beginning. We could go like this: a equals 1 minus 0.01 e to the minus q.
I think there's supposed to be an A beside the negative Q.
Okay, yeah. For some reason, when I put the formulas into this OneNote, sometimes it does weird things to them. It leaves things out. Okay. Because otherwise you could have just solved it for A and you wouldn't have needed implicit differentiation. But now the A and the Q are all tangled up, so we can't do that. So we'll come along and we'll go d by dq of both sides. We're imagining A is a function of Q. Okay, so on the left-hand side, we'll have to use the chain rule, minus QA, and then times d by dq of minus QA. And then on the right-hand side, well, it's just going to be 0 minus dA dq. So we're trying to find dA dq. Okay, so here we're going to have to use the product rule, right? Because we've got minus q times a, which is a function of q. So it'd be like if you had minus q times the sine of q or something. So that's going to give us 0.01 e to the minus qa times u prime is just going to be minus 1 times a plus, well, a prime is just going to be, well, you can just call it a prime, or I'll just call it d. I was calling it dA dq on the other side, so that's the same as a prime, right? Before we were doing y prime, now I'm just times minus q. Okay, so this is like u prime v plus v prime u equals minus dA dq. You could just call it a prime if you wanted, okay? Right? I just started calling it dA dq, so I thought I'd keep up with that. Okay, so we've got the dA dq here and here. So I think I'm going to distribute this so that to facilitate getting them both the dA dq's on one side. Yeah.
How do you get the dA dq from A?
Well, it's just a prime. It's the same as, like, remember when we were doing this yesterday? Because remember, we're doing d by dx of x is 1, d by dx of y, we were calling it y prime. Because we're taking the derivative with respect to x. And we're thinking of y as a function of x. So remember when we had this thing up here, you know, where we have to use the chain rule? Well, and I was comparing it to, I was sort of making an analogy between these two. Like y is some mystery function of x. So d by dx of y squared is 2y y prime. Just the way d by dx of sine x all squared is 2 sine x cos x. Right? That's what we were doing yesterday? Or no, Friday, sorry. Remember that? But on this page, instead of x and y, we've got q and a. And we want the rate that a changes with respect to q. So we want dA dq, which we can call a prime instead of y prime. So instead of writing a prime, I just started writing dA dq here. Yep.
Can you just multiply d over dq by a over 1, essentially, with dA over dq?
So sorry, what was that?
So like you essentially like just multiply the d over dq by a over 1?
Well, you're not multiplying it. It's an operator. It's like instructions telling you take the derivative with respect to q of whatever follows. So in a sense, it looks like you're multiplying it, but it's really just saying, well, I don't know what the derivative of a is with respect to q, so I'm just going to call it dA dq. Or you could, if you want, you can call it a prime. Okay? But it's just an operator telling you take the derivative of whatever follows with respect to q. Okay, so it's more like instructions. But because a is a mystery function of q, we don't know what dA dq is, or a prime. So we're just calling it dA dq. Okay? So I'm just, yeah, I guess maybe this one seems weird compared to the other ones because it doesn't have x's and y's, it's got these a's and q's in it. So I'll just neaten that up a bit. No, maybe I'll put the a in front. Minus 0.01 q e to the minus qa times dA dq equals minus dA. Okay, so we've got one here and one here. But this is part of this bigger thing here, right? It's being multiplied by it, so it's like it's all glued together. So maybe I'll bring this one over to the other side, because we've got to get both of them on one side. Remember, just like we did over here. Remember, we got both the y prime containing terms on one side. They were on opposite sides, right? And we rearranged it so that they were on the same side so we could factor out y prime. Right? Did some of you, were you not here Friday? People are looking like they've never seen this before. Were a lot of people not here? Or I can't remember when we started this.
We did that Friday.
Oh, Wednesday. It would have been, or Thursday, when? It would have been Thursday. I think if you did miss the lecture, some of the lectures, I think the lecture is on Moodle. Like the actual.
Is that the one you recorded?
Yeah, I'm trying to record this one too. I think I recorded that one. Or maybe it's just people have forgotten. Okay. So, yeah, I'm just an experiment to see if it'll work. So let's move that over to the other side. We'll add it to both sides. So that'll give us minus 0.1a times e to the minus qa equals 0.01 q e to the minus qa times dA dq minus dA dq. So I just moved it over to the other side. Well, I moved it here. Right? I just added it to both sides. Maybe people have just forgotten it. And now we're going to factor the ADQ out. And then we divide by, we just divide both sides by the residual, or whatever you call it. So that's all it asks us to do here is find this. So that's the answer. You can't simplify it because of that -1 in the downstairs, right? Whatever you do, don't try to cancel those. Please don't cancel those e's, because there's no e in the 1, right? I mean, this whole downstairs is getting divided into this thing, not just the first term, the whole thing. So that's all it asks us to find. So anyways, I guess this is Q here. Q is a measure of disease transmissibility, like how easy it is to transmit the disease. And A is the portion of the population ultimately infected. So you can see if Q is not very easily infected, I mean, if the disease is not very easily infected, like if it's got a small transmissibility, then, well, wow, it still looks like if 1 out of 1% or 1 out of 100 people, according to this model, you'd still get 99% of the people would get the disease. So I'm not sure. Anyways, but as it gets, of course, as Q gets more and more transmissible, it just goes right up to 100%. Everybody gets it. Anyways, that's all we had to do there. Any questions about that? Okay, now we're going to use implicit differentiation to show where the derivatives of inverse trig functions come from. So I'm assuming you've already studied inverse trig functions, like arctan and arcsine, but if you haven't, well, we don't really need to know much about them. There's two ways of writing arctan. You can write it as arctan x, or you can write it as tan to the -1x. On your calculator it says tan to the -1, but it doesn't mean 1 over. They're using that -1 notation in the sense of an inverse function, like a backwards function, not as a 1 over function. So that's one of the main things to know, is that tan to the -1 does not equal 1 over tan, at least not in general. So if y equals arctan x, then tan y equals x. So arctan x is an angle, the angle whose tangent is x. For example, arctan 1 equals 45 or pi over 2 radians, since tan 45 degrees or pi over 2 radians is 1. So if I just draw a little triangle, and let's say that's, oh, that should say pi over 4, I'm sorry, pi over 4 radians. Let's say that's pi over 4 radians, or 45 degrees, and this is pi over 4 radians. So it's an isosceles triangle. This would be like 1, there's your right angle, and that would be the root of 2. So the tangent of 45 degrees, or pi over 4, is opposite over adjacent 1 over 1. So it's just 1. Arctan 1 equals, well, if you're in degree mode, equals 45 degrees, or pi over 4 radians. Okay. So we want to find what the derivative of arctan is. And what we're going to do is start with tan y equals x. And we're going to differentiate it implicitly with respect to x. So we'll start with this, tan y equals x. Therefore, arctan x equals y. We're going to come along and go d by dx of both sides. Well, we already know what the derivative of tangent is. It's secant squared, right? So here we're going to say, okay, that's going to be, so it's like the secant squared, but it's d by dx, and that's not an x, it's a y, right? So this is some function of x. It's some mystery function of x. Well, in this case, it's not a mystery function. We know we have a name for it, but we still don't know what its derivative is. But we have to use the chain rule. So this is going to be secant squared y times y prime. Or if you want, you could call it dy dx. Because y is arctan x. It's going to be the derivative of arctan. And on the other side, we just get 1. So we're trying to solve for y prime, so let's divide by secant squared on both sides. Secant squared y. And that gives us y prime equals 1 over secant squared y. But, so we do have, so that's the derivative of arctan, secant squared y, of arctan x equals y. But we want it in terms of x. So we're going to use this trig identity down here. This is coming from that Pythagorean identity, remember? Sine squared x plus cos squared x equals 1. Well, if you come along and divide everything by cos squared, sine squared over cos squared is tan squared. This gives you tan squared x plus 1 equals, and 1 over cos squared is secant squared, because secant is 1 over cos. So that means up here, well, we can take this little guy here, one plus tan squared y. Right? So whenever in math two things are equal, you can just replace one of them with the other. So secant squared y is equal to 1 plus tan squared y. So I can just lift one of them out of there and replace it with the other. Right? Well, no, you could write that as 1 over 1 plus tan y all squared. And our object here is to get it back into terms of x. But look what we started with. We started with tan y equals x. So I can just replace tan y with x. So y prime equals 1 over 1 plus x squared. So, and y is arctan, so y prime is the derivative of arctan. So we've got a new derivative now. Actually, I probably should have gone back and done that logarithm. Remember we skipped over it? We'll come, anyways. And on the next page, I believe we're going to do the same thing with arc sine. But we're just going to, okay, we're going to return to this page in a minute, because I just, return next class. Because I forgot we have to go back and do logarithm. Remember I had the pages in the wrong order? Okay, this is the one that said we'd return to this. Well, it doesn't matter that we did the derivative of arctan first before logarithm. One doesn't depend on the other. Okay, so remember what logarithms are. They're exponents. So this y here, which is equal to log base a of x, is the exponent that you have to raise a to get x. Right? Everybody remember that? No? So, and if we've got log base e of x, well, remember that's the one we spell ln. That's an L, not an I, by the way. Or we call it ln. I don't know what you're supposed to call it, but that's what I would call it. Well, that's base e. So if ln x equals y, that means e to the y equals x. Okay, so this is called the exponential form. And the other one is the logarithmic form. But they're saying the same thing. And here it just asks us to make up some examples to verify. So, well, let's do log base 10, okay? Because your calculator probably has log base 10 on it. It should have log base e as well, of course. So let's say log base 10 is the one that's spelled just log. Does that ring a bell? That if it's just spelled logx with no base given, then it means it's base 10? Okay, so let's say log base 10 of 100 equals, well, what is it? What's the log base 10 of 100? Do it on your calculator. If you've got a natural logarithm or a log base 10. Anybody? What is it? 2, right? And that's the same as 10 to the 2 equals 100. Right? So that's your and the base wasn't written in there, but if it was, so log base 10 of How about 0.001? -3. Okay, so that means that 10 to the -3 equals 0.001, which is the same as 1 over 10 to the +3 is the same as 1 over 1,000, which is 0.001. Base 10. Okay, let's try it with the natural logarithm. The natural log of, I don't know, let's try 10. Let's see what that is. I'm getting approximately 2.302,585. Okay, so that means that e to the 2.302,585 should equal approximately 10. And you can check that out. Okay. These are just sort of in the way here. So it's in base E logarithm, the base E logarithm of 10 is the power that you have to raise E to get 10. Remember, E is just a number. E equals approximately 2.718. It's just a number. But it has that special property that it's its own, e to the x is its own derivative, which is why we use it. And the log, the natural log is also the easiest one to take the derivative of compared to other logs. Okay, so we're going to start with, it says start with a to the y equals x. Well, let's just start with e to the y equals x. E to the y equals x. So if e to the y equals x, that's the same as saying that the natural log of x equals y, right? Wait a minute, have I got that right? Yes, I have that right. Okay, so we're going to come along and go d by dx of e to the y equals d by dx of x. So we're just taking the derivative of both sides of this thing with respect to x. Now, in the first case here on the left-hand side, that's an x, and that's a y. So we're thinking of y as a function of x. Well, in this case, we know we have a name for it. It's called the natural log of x. But we don't know what its derivative is, but we have to use the chain rule, right? So it'd be like if you add e to the sine x, and the derivative would be e to the sine x times cos x. Well, this is going to be e to the y times y prime, right? We're using the chain rule. And on the other side, you just get 1. So that means y prime equals 1 over e to the y. But wait a minute, e to the y is x. That's what we started with. So y prime equals 1 over x. And d by dx of the natural log of x equals 1 over x. Now, if we, so that's this one right here. And that's the one we'll mainly use. If it was a different base, actually this should say log a. I should say that a is missing right there. Because we hardly ever use the any other exponent. But remember, if you remember way back when, we did this. If you look back in the notes, you'll see this. And of course, if we're using e as the base, then the natural log of e is 1. So we don't have to bother multiplying it by it, because it's just 1. But if it's anything besides e, then we'd have to multiply by it. So if you just do the same exercise, start with a to the y equals x, and go d by dx. You get a to the y times the ln of a times y prime equals 1. So you get y prime equals 1 over the natural log of a times y prime. Sorry, times a to the y. But a to the y is x. This is x. So that's where this one comes from. I generally never give you a logarithm, that anything other than a natural logarithm, but you might see it somewhere else. So I just wanted you to know about it. Or if you go on to take calculus 2 with somebody else, you might see it somewhere else. Okay, so we've got we've got a new derivative. The derivative of ln x equals 1 over x, and then we've also got